Welcome to Chapter 5. This chapter is all about dealing with trig identities. And this chapter may be unlike anything you've done in math so far. We're going to be showing that a lot of things are always true. We will be solving some equations, but for the most part, that's not what we're going to be doing. As a reminder, these are the trig identities we developed in the previous chapter. We have all of the reciprocal identities. We have our quotient identities. We have our three basic Pythagorean identities. And we have our even-odd identities. Okay? So the first things we're going to be doing here is we are going to be using these trig identities to simplify an expression. And one of the most useful ways of doing that, one of the easiest ways to do that, is to write everything in terms of sine and cosine. And every trig function we can do that with, because whether we have cosecant, secant, or cotangent, we can change these into a sine or a cosine. Tangent also does as well, because of our quotient identities. And it will usually make things look worse before it gets better, but it usually does work, okay? And then the rest of these identities, we developed by rewriting them in terms of sine and cosine. We had this first Pythagorean identity that came from the unit circle. And then to get this identity, you divide everything by cosine. To get this identity from here, you divided everything by sine, and it worked. So the rest of these identities you can think of as shortcuts. We got them by writing them in terms of sine and cosine, and we're just using the simplified form now. Okay, so let's look at an example problem. We want to use the fundamental identities and appropriate algebraic operations to simplify each expression. So I have sine x times cosine x times tangent x plus cotangent x. Okay, we can think of this as some number. These are things that are added together. Chances are we're going to be distributing. But the first thing I want to do is I want to rewrite tangent and cotangent using our quotient identities so that everything is in sine and cosine form. So I have sine x times cosine x times tangent is sine x over cosine x plus cotangent is cosine x over sine x. Okay, now let's think of this as a distribution. If I multiply this times this first fraction, cosines are going to cancel out, and I'll have sine x times sine x, which is sine squared of x. Now distribute here, sine x cosine x times cosine x over sine x. The sines are going to cancel out. I'll have cosine x times cosine x. So this is plus cosine squared of x. So already it is more simple, but it is not completely simplified. And that's because sine squared plus cosine squared is one of our Pythagorean identities, and it is equal to 1. So this is simply 1. This whole trig statement is always equal to 1. It does not matter what angle we are talking about, it is equal to 1. Okay, so let's try the same thing here. Secant x plus tangent x times secant x minus tangent x. Well, I can change these into sines and cosines, and I may end up doing that. But what I notice is I'm thinking algebraically too. I have two binomials that are multiplied together. They have the same two terms. One is a plus, one is a minus. Therefore, this is a difference of squares. And if I just multiply this out using that, I will have secant squared of x minus tangent squared of x. And to see if I can simplify this further, maybe I want to go into sines and cosines and end up getting a common denominator and so on. But if you look right here, we have an identity that involves tangent squared and secant squared. This is secant squared minus tangent squared. If I solve this that way, if I subtract tangent squared, I'll have secant squared minus tangent squared, and that is also going to be equal to 1. So this is 1. Okay. Now, let's do the same thing, sort of thing here. I have secant squared x minus 4 over secant x minus 2. You want to be really aware of difference of squares because it's actually a technique we're going to use a whole lot. Here I have something squared minus 4, which is also a perfect square. So I can factor the numerator as secant x plus 2 times secant, except I can't write, secant x minus 2. And this is over secant x minus 2. And to reduce a fraction, this needs to be put in parentheses, or it needs to cancel out as a unit. And I can reduce that and that. So this statement simplifies to secant x plus 2. Okay. Now let's do this one. I noticed that I have tangent squared and I have secants in here. And I also know that tangent squared can be written in terms of secant, and it will probably be easier if I have only secants in this thing. So what would tangent squared be equal to? Secant squared x minus 1. So what I'm going to do is, instead of writing tangent squared, I'm going to write secant squared x minus 1, and that's my tangent, plus secant x minus 1 over secant x minus 1. So this is here. I put the parentheses here so it'd be a little bit easier to see what was going on, but algebraically the parentheses don't matter here. And I can simplify to secant squared x plus secant x minus 2 over secant x minus 1. Don't let the fact that these are trig functions in here mess you up too much. This is the same pattern as x squared plus x minus 2. And if we can factor this, we can factor this. Here I'd be looking for two numbers that multiply to a negative 2 and add to a positive 1. So this would factor as x plus 2x minus 1. So this factors with secant x's where the x are. It's a matter of matching the pattern here. So this numerator is the same thing as secant x plus 2 times secant x minus 1 over secant x minus 1. And so those cancel, and your answer is secant x plus 2.